Hello, and thank you for your interest in our research. Recurrent connectivity is necessary for the formation of heavy cell assemblies, which are groups of neurons with particularly strong internal connections that represent memories at the network level. However, the biomolecular mechanisms underlying memory consolidation in recurrent neural networks remain elusive. To form a memory representation, synapses are strengthened or weakened by neuronal stimulation. The synaptic tagging and capture hypothesis, which we will call STC in the following, describes the consolidation of these synaptic changes by the transfer from an early phase to a late phase, lasting for several hours and days respectively. We developed a recurrent spiking neural network model combined with calcium-based early phase plasticity and STC. Our model naturally implements the formation, consolidation, and cue-triggered recall of memory representations. Furthermore, remarkably, we find that STC not only maintains but even improves the recall performance without requiring external stimulation. The neuron and synapse model that we use is shown on the left-hand side of the poster in the orange box. A leaky integrate and fire model accounts for the membrane potential and spiking of neurons. Postsynaptic calcium elicited by pre- and postsynaptic spikes drives early phase weight changes. Sufficient early phase plasticity then triggers somatic protein production, and if a synapse is tagged and proteins are abundant, proteins are captured, which finally alters the late phase weight. The total strength of a synapse results from the sum of its early and late phase weight. Employing the mechanisms for the neuronal and synaptic dynamics that I just described, we set up a network of 1,600 excitatory and 400 inhibitory neurons with an overall probability of connection of 10%. The synapses between excitatory neurons are plastic and described by the STC mechanisms, while all synapses involving inhibitory neurons are static. There is a background input to all neurons at all times. Particularly strong inputs are applied to specific groups of neurons to trigger the formation or recall of a cell assembly. To quantify the functionality of memory recall, we use two different measures, which are visualized in the figure on the center right. The first one is a coefficient describing the degree of pattern completion during recall with respect to the original learning stimulus. The other measure is the mutual information between the distributions of neuronal activity during learning and recall. In the center column of the poster, in the top panel, you see the mean synaptic weight within a cell assembly of 150 neurons. Our first finding from this is that STC raises the synaptic weight by the mere passage of time. At the same time, the early phase weights decay, which enables once again that they change. As a second result, we find that upon recall after 10 seconds, no substantial changes occur, but upon recall after 8 hours, weights are raised substantially. These changes in weights not only consolidate the memory, but have an improving effect on the recall quality, as it is shown in the bottom panel for an assembly of 350 neurons. Switching off the early phase plasticity during recall reveals two components. The weight increase by the mere passage of time constitutes a passive improvement, while the weight increase during recall constitutes an active improvement. To summarize, we developed and investigated a theoretical recurrent neural network model by which we could show that the interplay of spiking neurons, calcium-based synaptic plasticity, and synaptic tagging and capture accounts for the formation, consolidation, and recall of memory representations. In addition, we predicted that this interplay enables memory improvement. In the future, we want to test our predictions with more specific experimental data from multiple levels, for example from multi-unit recordings or behavioral experiments. Our second goal is to run our model on neuromorphic hardware to enable faster and more energy-efficient examination and also application of the memory improvement effect. You can find further results from our model, like variation of feedback inhibition, variation of the assembly size, the effect of an additional intermediate recall stimulus, and the parameter regime for passive improvement in our paper. You can find a link on the poster. Thank you very much for your attention. For more details, please have a look at our paper, and please feel free to contact us for any questions or comments.